Hello, I'm Jason. Welcome to the Linear Algebra Tutor. Here we're going to study something called NTuples and also matrix arithmetic. Mostly matrix addition is what we're going to talk about. So I want to introduce the topic of an ntuple early on because it's a very simple concept, but usually students will read about it and they're like, what does this mean? It's a big fancy word. I don't understand. You know, just like with any class you take, whether it's statistics or calculus or linear algebra, the definitions of very simple things can sometimes get in the way. So let's tackle this one early on. Let's talk about an n-tuple. Before we get to that though, let's recall from your algebra or from your geometry. You know, you've worked a lot with x, y pairs. You know, we plot them on coordinate axes, x comma y, right? So for instance, you can have an ordered pair called 1 comma 3, right? And this is two numbers. So the ordered pair 1 comma 3, we know that it's implied that it means x is equal to 1, y is equal to 3. The comma serves to separate those two numbers so that we know that they're separate. So it's not 13, it's 1 and it's 3. The 1 goes with x, the 3 goes with y. I know this is pretty basic stuff, but I'm leading to something. Now in three-dimensional space, you have x, y, and z, right? So I could have a point that would be 2, 4, negative 3. So we know because of the commas that the number 2 goes with x, the number 4 goes with y, and the number negative 3 goes with z. And so if I have a three-dimensional system, I can go x, y, z, and I can find that point in three-dimensional space. And because it's three-dimensional space, we know this is 3 numbers. All right? 3 numbers. Now, where am I going with this? A set of n numbers. See here, I've already given you 2 examples, right? Here's 2 numbers and here's 3 numbers. I'm going to generalize and say we have n numbers. However many numbers we have separated by comma, right, is called n, you guessed it, n-tuple, right? N-tuple. The word tuple, just to put your next question to rest, means ordered list. Ordered list. So now it makes total sense. It's very, very simple for you to understand, even though at first this term n-tuple seems very complicated. It just means ordered list of numbers. The reason there's an n in front is because frequently in linear algebra, we're going to be talking about, sometimes we'll have pairs of 2 numbers. So here in this case, this is an n-tuple, but 2 is equal to n, so it's almost like a 2-tuple, right? Sometimes we'll have 3 numbers strung together when we're dealing in three-dimensional space. This is an n-tuple where 3 is equal to n, so it's a 3-tuple. But sometimes we'll have 4 tuples and 5 tuples and 6 tuples. So in general, we refer to all of these lists of numbers as n-tuples. N can be whatever you're dealing with, whatever problem you're working with. So if you read in your book, whatever book you're using, eventually you're going to come across the topic of n-tuple. In your head, just replace that word with, that's a list of numbers. A single list of numbers. This is not a rectangular matrix. Well, it is kind of a rectangular matrix where we have 1 row, but it's not a big giant square matrix like we've been talking about matrices so far. It's an ordered list of numbers. And the n just means that sometimes we'll have longer lists than others, basically. So in general, if we have something, we're going to call it u for now. We're going to call this n-tuple u. If we have a list of numbers like a1, that's a number, a2, that's another number, dot, 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 a sub n, that's another number, all separated by commas. Notice the commas here. Then we can call this an n-tuple. In this case, we don't know how many numbers we have. It's just a sub n. That's the maximum number that we have. So we're just going to call it an n-tuple. All right. Now we can write this n-tuple. See, so far we've been writing it as a separation of numbers with parentheses and separated by commas. And that's why I kind of drew your attention earlier here to something you're really familiar with. X comma y, x, y, z. Those are things that those are n-tuples that you're already really familiar with, right? But in general, if we don't know how many numbers we're dealing with, or if it depends on the problem, then we might write it like this in terms of parentheses and commas. But see, now we're in the realm of linear algebra, so we're going to want to represent things as a matrix. So in terms of linear algebra, we might write this n-tuple u as a column matrix. So maybe A1, A2, dot, 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 A sub n. Notice what I've done here. All I've done is take these values, whatever they are, and arrange them in a column. So it's a matrix now. Notice there's no commas anymore. There's no commas anywhere in here. All we have is number, 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 and however many numbers in between going to A sub n. We're calling this a column matrix. It's no different than any other kind of matrix you study. It's just a matrix. It just so happens that you have n rows and a single column. So because it has a single column, we call it a column matrix. All right, so we can represent this n-tuple, this listing of numbers, as simply a single column matrix with each number going down vertically like this. Put the matrix brackets, drop the commas, boom, you have an n-tuple. All right, but you can also describe it, you can also write it, I should say, can also write it, the n-tuple, as the following. We can also write it, there's nothing preventing us from doing so, we can take this n-tuple that we have here and take its transpose, which we've already talked about. So this guy, if we put a t here, what did we say we did with a transpose? We turn the rows into columns and the columns into rows. And since there's only one column here, we just make it into a row. A1, A2, dot, 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 A sub n. So this is, I want you to convince yourselves, this is the transpose of this n-tuple u here, because for transpose, we take the rows and we turn them into columns, right? Or equivalently, we take the columns and switch them into rows. But since there's only one column here, this single column of numbers just becomes a single row in its transpose. So we've done a lot of hand waving because I haven't really given you a great example for why n-tuples are very useful. But you're going to have to trust me. Very, very soon we're going to talk about something that I think is very, very practical that we're going to use n-tuples for a lot. But really I'm trying to introduce the terminology to you. Basically, an n-tuple is a listing of numbers, right? So you can, in terms of algebra and geometry, are used to listing these things inside of parentheses with commas, and you just have the numbers listed. That's what we typically call an n-tuple in geometry or whatever. But in linear algebra, we're going to either write it as a column matrix or a row matrix, which are no different than any other kind of matrix. They're just a listing of numbers. In this case, you list it as a column. In this case, you list it as a row. Notice there's no commas in here. We drop the commas when we're writing matrices, all right, which are n-tuples. So we drop the commas. We just put the elements in there, there. All right, so basically your standard x, y, z, you can write it as a column or as a row matrix. That's the bottom line. All right, so I want to move on from that. We're going to come back to n-tuples in the next section when we talk about vectors, or in the next couple sections when we talk about vectors. But for now, let's talk about adding matrices. I want to cover it now because it's very, very simple. So the bottom line is you can only add matrices together. If you have matrix A and matrix B, you want to add them. You can only add them if they're the same size, right? Because when you add a matrix to another matrix, you're taking each element in its corresponding location and you're adding them to arrive at the third matrix. So they have to have the same dimensionality, same number of rows, same number of columns, or you cannot add them together. It just doesn't work. So basically, if you have matrix A, for instance, and so we have 1, 2, 1, 1, 0, negative 4, like this. And then we have matrix B. We have 0, 1, 0, negative 1, 1, 2. Notice that matrix A has 3 columns, 2 rows. So think of it a different way, 2 rows, 3 columns. So it's 2 by 3. This also has 2 rows and 3 columns. So the dimensionality of those two things match. So because of that, we are allowed to add them together. A plus B, you would say, is equal to, and you just find the corresponding elements. 1 plus 0 gives you 1. 2 plus 1 gives you 3. 1 plus 0 gives you 1. 1 plus negative 1 gives you 0. 0 plus 1 gives you 1. Negative 4 plus 2 is negative 2. So you see we take the corresponding elements of the matrix and we arrive at 1, 3, 1, 0, 1, negative 2. And we can add those together. So now let me introduce, along the same lines, matrix C, 1, 0, 1, and matrix D, 2, 2, 2. Now, don't get scared that it's listed as it's represented as a column. This is just a column matrix. It's got 3 rows and 1 column, 3 rows and 1 column. So if we want to add these guys together, we can say C plus D works just fine because the dimensionality are the same between them. and I have to represent the answer in column form. 1 plus 2 gives me 3, 0 plus 2 gives me 2, 1 plus 2 gives me 3. So the answer is 3, 2, 3 represented as a column matrix. Now, what if we try to do something like add together A plus C? Well, we go up to A. This is what A looks like. This is what C looks like, and there's no way that we can add those together because the dimensionality is different. We cannot find corresponding elements in which to do the arithmetic because the dimensionality, the rows and columns, are not exactly the same. So if somebody tells you try to add these things together, you just say it's not possible. You just write it down. It's impossible or it's undefined or something like that. But you cannot do that. The final thing I want to talk about before I get into kind of the last part of my lesson here is notice that I arranged C as a single list of numbers in a column, and D in a single list of numbers as a column. So you can call that a matrix. It is a matrix. It is 3 rows and 1 column. So it's 3 by 1 matrix. That's what it is. But because we've already talked about NTuples, I want you to start seeing this as an NTuple. It's a listing of numbers. It just happens to be represented as a column in this case. Notice we said NTuples is just a listing of numbers, right? And we can arrange it either in column form or in row form. So in this case, you could call this an NTuple or a 3-tuple if you want, because it's only got 3 elements. You can call this an NTuple, or if you want to be more precise, a 3-tuple because it has 3 elements as well. I'm trying to kind of weave the terminology in as we go along so it's not such a shock when you read it on a test or whatever. All right, so that's how you add matrices. You basically can only do it if they're identical in terms of their dimensions. And now we want to learn how to multiply a matrix by a scalar. All right, by a scalar. And what I mean by that is, let's say we have that matrix C is equal to 1, 0, 1. Right? And then we want to do something like, let's say the number 5, that's a scalar, times the matrix C. That is defined. That's totally fine. Whenever you see a scalar like that multiplied by a matrix, all you do is you multiply the scalar by every single element inside that matrix. So 5 times 1 gives us 5, 5 times 0 gives us 0, 5 times 1 gives us 5. And so this is the matrix C multiplied by 5. We just distribute, basically, if you want to think of it as distribution, that guy into everything. Now, if we change it up and we say we have matrix A is 1, 2, 1, 1, 0, negative 4. If this is our matrix, and then we want to define matrix 2 times A, again, that's totally okay. When we multiply a matrix by a scalar, we just go to every element. 2 times 1 is 2, 2 times 2 is 4, 2 times 1 is 2, 2 times 1 is 4, 2 times 0 is 0, 2 times negative 4 is negative 8. So we get 2, 4, 2, 2, 0, negative 8. So again, adding matrices together, very simple. You add them element by element. You can only do it if the matrices match in dimensionality. Multiplying a matrix by a scalar, very easy. Just multiply every element by the scalar that you care about. And now I want to list, before we close, a few properties. These are things that are useful to know. I don't really think you should memorize them, but I think it helps us understand what we're talking about. The matrix A plus the matrix B, because of the way we've defined matrix addition, has to be equal to matrix B plus matrix A. And if you think about it, that makes sense because we're adding element by element. And since we know that 3 plus 2 is 5, and also 2 plus 3 is also 5, that if we reverse the order of the matrix addition, since we're still adding corresponding elements of the matrix, we're going to get the same result. That's what that's telling you. All right? That's also called the commutative property. That's what that's called. All right, now the next thing we want to talk about is what if we have matrix A and we add it to matrix B? We do that first, that's why it's in parentheses, and then we get the result and we add it to matrix C, right? The same thing happens if you take matrix A and add it to B plus C like this. You see the difference in what's happening here. Here, if I add A and B together first, and then I add matrix C, I get the same result as if I actually take matrix B and C and add them first, and then add matrix A to it. So when you're talking about expressions that involve matrices, the parentheses and everything hold just fine from regular old algebra. You have to do what's inside the parentheses first. So basically, when you have three matrices, what this is saying is it doesn't matter the order in which you add them together. And that's the same, it basically comes about because of the same rules of addition. 1 plus 2 plus 3 is the same thing as 3 plus 2 plus 1. It doesn't matter how I rearrange the order of the addition with numbers, so it's certainly not going to matter with matrices because I'm adding these corresponding elements together with A and B. And that has a name, and that's called associative. You probably remember some of these words from basic algebra. All right, now here's a couple of other things that you may, these aren't really getting harder, but they're things you probably wouldn't realize unless we listed them. If I have a scalar that I'm going to call k, and I have another scalar called m, and I'm going to multiply it by a matrix A. So what has happened here is I have a matrix A, multiply by a scalar, get the result, and then I take that and multiply by a different scalar. So m and n are both different scalar numbers, right? So if I do it this way, I get exactly the same result as if I multiply the scalars together first and then multiply by the matrix A. So here, for instance, if I take this and multiply this matrix by the number 2, let's say, and then I get the result of that, and then I multiply that matrix by the number 5, it's the same answer as if I take 2 times 5, getting 10, and then multiply by the matrix. And that's basically comes about because of how multiplication works. It doesn't really matter the order in which you multiply things. So when you're multiplying by a scalar, because of the way it's defined, it doesn't really matter if you're going to multiply by two scalars, the order in which you do the multiplication. You're going to end up getting the same number. That's what that means. And then the final one I'm going to share with you here is if I have a scalar k, and I multiply by the sum of two matrices A and B. These are matrices here. And then I get the result of that and I multiply by a scalar. It's going to be exactly the same thing as if I take that scalar multiplied by matrix A, scalar multiplied by matrix B, and add them together. And this looks a whole lot like distribution, in terms of algebra. You take the k and you distribute it in, and you can think of it in terms of that. It only works because k is a scalar. So basically, if I sum two matrices together and then multiply by the scalar, it's the same thing as doing the scalar on each of these matrices and then adding the result. And that's because the property of addition and the property of multiplication in general doesn't really matter the order in which it's done. So we say it's linear, and because of that, it doesn't really matter. You can kind of treat it as distribution. Now, this only works when k is a scalar, a number, right? If k is another matrix, then things are different, because we're going to get to matrix multiplication in a few minutes, and as you might remember from earlier classes, matrix multiplication by another matrix is a little more involved. So we're saving that for the next section. But in this section, mostly what I wanted you to know is a few core concepts that we're going to use repeatedly throughout the course. A set of numbers, we typically call it an NTuple when it's just a listing of numbers. It's also a matrix. It just has, one column associated with it. So we write an NTuple as a listing of numbers, or you can write them horizontally, and we'll have occasion to do that. You'll see a little bit why later. So we can write them like that. We also talked about matrix addition. You can add them together as long as they're the same size. But you cannot always add matrices together. If they have different dimensionality, it's not going to work. And then the final thing we talked about is multiplying a matrix by a scalar. You just basically kind of distribute that multiplication in throughout every element and just go and do it that way. And then we listed the properties here, which we've gone over recently. So we're tiptoeing in. I know that you've seen a lot of this material before, but I'm trying to solidify it for you so that when we get to something that you don't know, you'll be brought right up to speed and right there ready to tackle wherever the limits of your knowledge is. And then we'll probably get there pretty soon for most of you guys who are studying linear algebra for the first time. So stick with me here. We're going to go into the next section. We'll review and talk about matrix multiplication by another matrix. And then we'll get into some other topics that typically are covered in linear algebra courses, which are extremely important and useful. So follow me on this journey to the next section. We'll tackle matrix multiplication by another matrix.